All right, hello everyone. Thank you for taking the time to join us today. My name is Jordan Larson, and I will be your host for this NASA Technology Transfer Program webinar on robotic assembly of photovoltaic arrays. Our presenter today is John Carr, and he is joined by fellow inventors Austin Bumbleo and Furman Thompson. Following John's presentation on the technology, I will be giving a very brief presentation on how NASA licenses technologies to outside organizations. Before we get started, I would like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them in the little chat box down in the lower right-hand corner of your screen, and we will answer them during the Q&A session at the end. So at this point, I'm going to turn it over to you, John.
Right, thanks so much, Jordan. Before we get started, we're going to do some quick introductions. I'm Dr. John Carr. I'm the principal investigator for the project you're going to hear today. My educational background is from Iowa State University, where I spent a lot of time working on thin film solar cells and thin film solar arrays, which, as you'll see, is really the backbone, the core of the topic we're going to talk about today. I spent a few years in industry at a Fortune 500 semiconductor company called Micron Technology, and then moved from there here to NASA, where I spent the first part of my career as a technologist in the lab, doing this sort of PI work, technology development, which certainly I still have at least one foot in, and of course that's why I'm here presenting today. After my time in the lab, I spent a couple of years as the Marshall Space Flight Center Deputy Chief Technologist, where my role was to support the Chief Technologist in helping others at our center develop new technologies, right? How to grow and build on your ideas. And currently my title is the Advanced Propulsion and Technology Systems Formulator, which is essentially a very ancillary or similar role where I'm looking at for the center, what are the next things we want to go and do and that we should go and do to develop the right technologies at the right times. So it's good to meet you, good to be with you all here today. I'm going to let my inventor team introduce themselves as well. We'll start with Austin Bumbleo.
Hey everyone, my name's Austin Bumbleo, and I have a bachelor's degree in electrical engineering from the University of Alabama here in Huntsville. And I'm an early career employee with NASA. I've been at Marshall since early 2018 as a co-op and recently converted over to full-time earlier this year. So I'm glad to be here and look forward to sharing this presentation with you all.
All right, thanks, Austin. And now let's go over to Furman Thompson.
Hey, everybody. Hope you can hear and see me well. I'm Furman Thompson. I'm kind of excited to be joining you guys today and talking a little bit about the technology here. I actually started with NASA around 2010. I came in under the program we used to call the co-op program, which is now, I think, Pathways. And so I co-opted in as a sophomore, started making trips back and forth. I was at North Carolina A&T working on getting my bachelor's degree in electrical engineering. And so I would come back and forth from Huntsville to Greensboro, North Carolina, and working on, I started out in the AAA parts packaging and fabrication area. So I was kind of a double E guy working on electronic parts and packaging, and started out with the capability there. They have capabilities to kind of build up electronic parts, circuit boards. They develop the cabling. They do a lot of testing and things. So I got my start there, and then I kind of rotated around, got some experience working in the materials area, developing materials for printed electronics. I work a little bit of work with Resource Prospector Lander. And so ultimately, when I returned back to my branch, I started helping out with a lot more of the testing and kind of worked myself into sort of a SME role in the printed electronics area, where what we were doing is a lot like what John was talking about, trying to understand some of those capabilities, the new advanced technologies that the center is interested in, and how do we bring it in. We were looking at additive manufacturing and also printed electronics. How can we take those two fields and increase our knowledge and our capability? So I supported that area as sort of a focal area champion, and I worked across teams, working with other centers, Ames and Langley and different centers, working to try to increase that capability. And a lot of that work is still going on today in space manufacturing. And so a lot of my background, starting really in high school, was in industrial controls, robotics. And so a lot of the technology that we're talking about today, you'll see, robotics and industrial things being used. A lot of that, I was kind of the guy that helped kind of put the hardware together, and then got together with John and Austin. Austin was an intern at the time, so he helped do a lot of the programming and helping us get the steps and things right. And then John was kind of the big vision guy. So it's really nice being able to be here and share with you guys. And right now I'm serving as a lead systems engineer for a project called Impact. It's a Moon to Mars planetary autonomous construction technology. So it's taking that additive manufacturing, and now we're trying to move that to the lunar surface, to the moon, to start taking some of those capabilities to other places. So good to be with you guys, and appreciate your time. Thank you.
All right, thanks, Furman. So we're going to jump into it. As Jordan said, this is about robotic assembly of photovoltaic arrays. Now, the first thing I'm going to do is actually show you a video. Bear with me as I pull this up. I'm going to So that was the video you just saw. And let's get into the talk. I want to start by motivating the core work. Okay, now the core work here is for thin film solar, right? To be clear, the patent and the main topic we're here to talk about is actually that robotic assembly that you just saw. But really two objectives here. One, two birds with one stone. A lot of you may be interested in the core thin work, so I want to use this platform to make sure you understand that. But more importantly, I think it's really useful if you all can understand why we were motivated to come about this invention, what we plan to use it for, why we need it. right? And so that'll help you understand it a little bit more, understand where we're coming from, and hopefully help you, frame in your mind some further applications that you may be interested in. So let's motivate thin film solar here at NASA. And in short, we are designing for small spacecraft, at least in the beginning. Okay, now why small spacecraft and why thin film solar? Well, simply put, small spacecraft are power starved. Okay, anybody who's worked with small spacecraft know that surface area, mass, and volume are extremely limited resources. Okay, and this causes a push, a pull, a fight between subsystems, right? And ultimately, capability becomes choked. Typically in spacecraft design, we have some objective, some goal to go do, which is, let's say it's a science instrument, a payload that we want to take and go do some measurements. And we design a bus around it, a bus of appropriate size, for all the supporting equipment, for all the power it needs, et cetera, et cetera. The paradigm in small spacecraft is slightly different, though that remains somewhat true. We're now trying to do it with a fixed bus or a relatively fixed bus, right? What can we fit in a 3U, a 6U, a 12U, or other appropriate small spacecraft? And so if I was to sum up the challenge in small spacecraft in one question, it really comes down to, in my mind, how can we do more from less? And certainly this is true for the power system, especially batteries and the power generation system, right? Electronics are always shrinking, becoming faster, more powerful, utilizing less electricity, less power, and from smaller packages. But doing more for less, especially for power generation, is a difficult challenge. And so we at Marshall have been working on a thin film solution to solve this. Okay, essentially, we're looking at solar sails. These are large gossamer propulsion sails, right? For those of you unfamiliar, they use reflection, photon reflection, to actually generate thrust in space. This particular sail is about 86 square meters in size, and it's just a couple of microns thick. So very low weight, stows into a small volume, and then deploys into a very large area on orbit. So we're looking at these large gossamer sails and realizing, hey, this is a really good substrate, especially when coupled with thin film photovoltaics, a lot of work of which is going on in the community, to replace a thick film solar panel. This happens to be a CubeSat solar panel, which is why it might look a little bit different than what some of you are more akin to, but replace a thick film panel with a fully thin film, fully flexible version thereof, and that's a sample assembly. Okay, and then we take those assemblies and we create arrays out of them. This happens to be an array that we flew some ZeroG experiments. You can see it's coming out of a 1U CubeSat in this case. And we're solving that problem, doing more from less on small spacecraft. However, it's more than that. We want to grow from this. Small spacecraft is that initial path, right? It's that initial way in the door, that seat at the table, for a good, strong application of thin films that we can then build and grow off of. And so indulge me on this slide just for a second here. Did you all know that only one mission has visited the ice giants, particularly Uranus and Neptune? And this mission was Voyager 2, which did a brief close approach and with 1970s era technology, right? And so it's said that a lot of our solar system's mysteries remain locked away in the ice giants, which we just haven't had the opportunity to study in the depth that we would like to. And this is because deep space missions are hard. They're complex, they're costly, and a big part of that is they all utilize nuclear power. Every mission beyond Jupiter utilizes nuclear power, and nuclear is very costly. It's more difficult to integrate, and its use has socio-political implications. Now, most importantly, the most common fuel we use, plutonium-238, is extremely scarce. We in the United States only produce 12.6 watts. It's a few grams worth of plutonium a year. And we have scaling plans at Oak Ridge to reach up to 47 watts per year within the next decade. But mind you, it's not just deep space missions that are competing after this, right? It is those radioisotope units for powering those deep space missions, but also planetary missions, rovers, especially our Mars rovers and others, and radioisotope heating units, right? Applications like surviving the lunar night are going to require those. And certainly not just NASA and our science and exploration mission, also on the Army and the DoD side that are all competing for this very limited resource. So what if we can offer another option to power these deep space missions? So we call this solution the power sail, and it's essentially taking those thin film assemblies that I just showed you and integrating them back onto large solar sails. So instead of those smaller solar arrays that we're creating for small spacecraft, these would be enormous thin film solar arrays that then could take spacecraft deep into space without the reliance on nuclear power. And so for those of you aware of our solar sail missions, you'll know these names. If you're not aware of these, just look at the sizing is where I want you to focus. But NEA Scout is a solar sail that's built and about to fly on Artemis 1. It's 86 square meters, and it could be a 20 kilowatt class power sail at a very light weight, greater than 1,000 watts per kilogram. And so this enables non-nuclear power out to Saturn. And then if you scale that to Solar Cruiser is a funded solar sail, which will fly in the beginning of 2025. It's about 1,400, 1,550 is actually the number that we're using right now. This could be a 350 kilowatt class power sail at even better specific power rates, enabling non-nuclear power out to the ice giants. Okay. Now, all of this is coming together in that motivation in how do we fabricate a solar array of that size? We're talking an Olympic pool, 2 Olympic pools, right? It takes you a little bit to get oriented to that picture, but this is an aerial view of an Olympic pool. Could you imagine one by one putting a solar cell, connecting the solar cells up, routing the bus power, right, including diodes, whatever we need to do by hand, very tediously one by one here. And you know, this would be a little bit smaller than Solar Cruiser. So imagine going to 1.5 this, to 2 this, and higher. And coming back to the small scale, coming back to those CubeSat small spacecraft, it's not just about a very large asset, but also a large number of small assets. As we look at swarms in the hundreds, in the thousands, and concepts for swarms of tens of thousands, how do we fabricate a very large number of these thin film assets? Okay, and that's the technology that we're here to discuss. So, you know, hopefully that gave you a little bit of flavor of the thin films. And you can see application in those outside of this assembly process. But more importantly, hopefully that motivated you and led you down that path that we took to come to PAPA and really to invent this assembly procedure. Okay, so as you've probably garnered, we call this project PAPA, or Print Assisted Photovoltaic Assembly. But as you saw from the title side, the patent is actually entitled Robotic Assembly of Photovoltaic Arrays. So, you know, generally you look at the patent, you're going to see that title. But if you look at our white papers and as we publish work on this, you'll probably see a little bit more flavor of PAPA or some variation thereof. So what I want to do is play that video for you once again, now that you kind of have this mindset of what we're trying to do. Hopefully it's not too tedious to see it twice, but it's I like that repetition so you can really understand it. So I'm about to hit play again, just to check your speakers real quick. Okay, and this time I'm going to talk a little bit over it. And I got slides to break this out, but what you're seeing now is we picked up solar cells with our pick and place tooling, and we're actually laying down an adhesive. Now, this isn't technically a third-party adhesive, which I'm going to reiterate later, but we spray it down, and then you can see we drop the cells right in place where we need them. So this actually embeds the cells into the top layer of a polyimide substrate, which you can see down there on the platen. And if you can't hear me, if the music's too loud on your side, no worries. I'm going to go over this again step by step. So right now we're printing a sealing, seal the edges of the cell, as well as what we call an interconnect bridge, which I'll give more information on. And now you're seeing just a dry time. The substrate's actually on a heated platen, such that it can real time dry out each of the layers. And now we've picked up a new tool head to go and actually dispense silver ink. We've got it in a nice pattern here for both redundancy and ease of the manufacturing process. And so this is interconnecting the cells together and then enabling, for routing of that power off of the solar panel. So now we've got a cure time for that ink. This is a low temperature cure. And then we're going to pick up a spray head to go and encapsulate with a polyimide. This is just clearing the nozzle. And a nice encapsulation to fully laminate, if you will, these cells and interconnects. Okay, so let's break down this process. So the Papa technology objectives, right? The objectives of that robotic assembly that I just showed you are twofold, and I've hinted at them throughout. But certainly the first one in the near term is to reduce panel cost reduction, and like I really hit at, enable those large scale productions of either single assets or many assets, right? Essentially thousands of square meters of thin film solar array assets. Now coming back to the panel cost reduction, we're estimating that we can reduce touch labor costs by a factor of 10. When we look at our thin film solar array procedure and what it costs to have these done via touch labor, we're in the range of $250, $350 dollars per watt for the touch labor. Which when we remove this, we think we can get our touch labor down in the range of like $25, $35 per watt, about a 10x reduction. Okay, now also coupled with this are more long-term goals. And I got to move just a couple of these windows here. So you see there, we're laying the groundwork for the capability for in-space solar array manufacturing, right? In the near term, reduce panel costs and enable large-scale production terrestrially. But in the long term, enable the capability for in-space solar array manufacturing, right? So a little bit nearer term within this long-term goal, I know it's, stay with me here, right? On-orbit assembly, maintenance, and repair, right? So this would be bringing up pre-assembled modules and then on orbit, putting them together. Marshall is a real big player in OSAM, the on-orbit assembly service and manufacturing service and repair. And in fact, the OSAM workshop is going on right now at Marshall as we speak. Now, longer term, we envision then a fully printed in-space manufacturing of these thin film solar arrays, meaning not bringing up pre-assembled or prefabricated modules to be assembled on orbit in space, but actually bringing up raw materials or even utilizing some in situ materials to be able to fully print thin film solar arrays, solar cell, substrates, coatings, interconnects, and then eventually the deployment and structural system that needs to surround it. Let's see the next slide here. Okay, and beyond. And I got sort of a stray picture there. Ignore that for now, but you'll see in a lot of my presentations, I like to always have this ... and beyond, right? Because I think it's good for us to sort of dream a little bit and think, what else could this be used for? We definitely have our target application of small spacecraft and our longer term target scaling goal of the power sail, right? And we see opportunities to then grow that to in-space, on-orbit manufacturing, assembly, and repair. But we also see opportunities to integrate into spacesuits, right? To provide emergency power, to provide trickle charge, as we're doing longer and longer EVAs, which can become limited by power availability. And in a similar case, integrating directly into planetary habitats, right? Something that can fold, can roll, can stow with the habitat, and then simply deploy as a single unit once on the surface, lunar, Martian, whatever. And then most importantly, repair. And certainly that's a picture of terrestrial units. But we know as we go to the moon and as we go to Mars and we're looking to sustainably stay, we're going to see damage, right? We're going to see micrometeor hits. We're going to see, eventual dust degradation that we can't overcome with cleaning. And so being able to, repair, meaning you print a new solar array, hook a new solar array directly in situ, maybe not using in situ resources, but in situ, is going to be important in the long term for our sustainability push. Okay, so let's go through that process that I showed you in the video. So this is a sort of a simple block diagram, if you will. That first step that you saw, we were laying down an adhesive. Usually I put adhesive in quotes, and I'm going to talk about that in a minute here. But we lay this down via a micro spray print. You saw directly on top of that, then we grabbed solar cells and placed those down almost immediately to embed those actually in the top layer. And I can't say too much more than that, as there's some proprietary processing going on there through one of our contractors. But let me leave it at that, and we can discuss that more offline. The next thing we do is we print an interconnect bridge, okay? And so that bridge actually seals the edges of the cells to make sure we don't get wicking on any subsequent steps, and gives us a nice, even surface to then print step number 4, which is adding interconnects and the power buses. We lay these down via a dispense print, okay, and you saw just a silver ink, a low temperature silver ink. And then finally we add a cover, and this is again laid down via a micro spray, and it encapsulates and protects, both electrically and environmentally, the top sides of our films, of our solar cells, and our interconnects. Now, a couple of key notes I wanted to mention is that there's no third-party adhesive used, right? So when I say we're laying down adhesive, it's not an RTV, it's not a glue and epoxy or anything like that. It's actually the same material set, the same polyimide set that we're using to essentially enable us to embed these cells in the polyimide substrate. But it's important that there's no third-party adhesive. It cuts down weight, it cuts down thickness, and it's really advantageous in thermal cycling, where we don't have another material, another coefficient of thermal expansion in there to worry about, where we might get delamination or we might get micro tears from the stresses. It's also important to note that we're cell agnostic. Okay, we're designed around a unit cell, and really that unit cell has plenty of room to move depending on the end application. But my point here is that you don't have to have a specific cell. Largely, we can integrate all current thin films, and we're set up well for future thin films. The devil's always in the details, and we'd be hard pressed to say, no matter what the cell, we can integrate it into this process. But we've designed this to be cell agnostic, to be able to accept a large number, if not all, thin films. And there's several cover options, and I think that this is one of the key areas of growth going forward. But we currently have a couple that we use, and generally, so long as it's solution processable, it can be integrated. Okay, and so to walk through our robotic setup here, I just wanted to label a couple of things to help you all get sort of oriented. You can see at the top right there, kind of in the top middle, that's our robotic arm. And you can see that was really the workhorse for everything that was going on. It's supported on the left there by some custom cell trays, right? That's where we hold the cells. It comes over and picks those up. We've got custom tool heads on the right that the robotic arm can come and pick up. Certainly the pick and place tool that I just mentioned, but also dispensers for ink, spray nozzles for polyimides and the like. And then everything is built on a substrate, which is attached to a heated platen. And that substrate, we currently start with a roll of polyimide that has a backer on it. But there's options beyond that. We've also looked at, you could spray your own substrate, right? And just start with a backer. And certainly there's room to grow there as well. Okay, and then really taking a look at that step-by-step process in some of these main steps, so you can see pictures going back. This camera, this GoPro camera on the left, this is the view during the fabrication process. And so you can see that quote unquote adhesive being laid down. You see just after the cells are placed. Now we're going in the bottom left and printing those seals and bridges. And then finally, we have the printed interconnects that you can see being started in the bottom right, but in the top of the bottom right picture. And of course, not shown here would then be that encapsulation step. It's hard to see, because that polyimide is so thin, but you kind of see that sheen come out as everything gets encapsulated and coated. And we're able to make modules. These are some pretty basic sample prototypes. You can see one unfolded on the left and then folded up on the right with semi-hard creases into the silver inks. And we've tested them, pre, post, and then a little bit of environmental testing. So those of you that like to see the data, there's 3 curves shown here. We have as fabricated in blue, post that folding and unfolding in red, with essentially no difference between the two. And then post cycling in black. We actually did some thermal cycling on these, which is the highest risk environment. And I'm going to talk about that on the next slide. And what you actually see is a little bit of improvement, even past the post fabricated, which most likely what's going on is this interface between the printed ink and the solar cell bus bars. There's a little bit of sintering, a little bit of annealing is probably a better word there, cleaning up that interface and giving you slightly better connectivity there. Okay, so current status and next steps. I believe this is the last slide before I'll turn it over to Jordan and questions. I wanted to mention that our by hand assemblies, right? These are our touch labor assemblies, the core of the technology, have been tested through ground chambers and MISTI FF, the MISTI flight facility, to TRL 7 for LEO. And we actually have a LEO array level demonstration in 2022. Now, this is important to mention because the PAPA assemblies, the robotic arm assemblies, use all the same material sets, the same solar cells, the same everything, to be informal there, with the highest risk that we see in a response change due to the process change being that thermal cycling, right? So we don't expect radiation to change. We don't expect UV to change. We don't expect atomic oxygen to change. It's really that thermal response that is at the greatest risk. So we've brought down that risk by already testing the PAPA assemblies through thermal cycling. Certainly, I wouldn't claim TRL 6 or TRL 7 until we really put a PAPA assembly through more environmental testing. But we don't expect any surprises there. No other environmental changes suspected. And MISTI FF, I think, is going to be the cheapest and most viable way to go and do that, and definitely is something that I have my eyes on, going forward. And I think the next steps to development really should focus around scaling. You see, in our lab, we're working in that 2, 4, 6 type sizes, and really we need to then grow that out, right? How do we get PAPA to be mobile, right? To be able to build up, say, that 1,000 meters squared, that 10,000 meters squared solar array. And certainly there's always mission specific and perhaps in-space specific applications that I think we should focus on the next steps. And so to that end, I wanted to let you know that Marshall remains open to collaboration. Certainly we support, direct licensing. If there's a company out there that just wants to grab onto this and run, sort of with that firewall, without that direct partnership, we're open to that, but definitely wanted to let you know we remain open to collaboration through partnership, writing proposals together, and anything that you all guys see as good next steps make sense for you to grab onto this and move it forward. Okay, Jordan, with that, I'll stop my portion and let you finish up, and then we'll take questions.
Excellent. Thank you, Dr. Carr. We've received a number of questions throughout the presentation. I just want to remind everybody that if you have a question, please feel free to submit them in the chat box down here at the bottom left-hand corner or right-hand corner. And as promised, I will present a brief overview of the technology transfer program. Our office evaluates any new and novel inventions developed by NASA and determines if they have any uses outside of government work. And our agency sorts through hundreds of new technology reports each year and has compiled the best into our patent portfolio, which can be viewed here at technology.nasa.gov. We've went ahead and arranged everything into 15 different categories where you can search and stuff in sensors, manufacturing, optics, propulsion, and more. If you're looking for something a little more specific, you can actually search by keyword as well. We also have a pretty large software catalog where we have around 1,000 different codes that we give out for free. You can find those at software.nasa.gov, and it's set up the same way where you can browse by category or by keyword. Next slide, John, please. Thank you. And we have 3 different licenses available. You can have a commercial license, which is available in exclusive and non-exclusive. We have an evaluation license, which costs a flat $2,500 and lasts 1 year. It's a great way to test drive the technology in case, make sure it's a really good fit for your company before committing to a commercial license. And then we also have a startup license, which is for startups that are less than 24 months old, and there are 0 upfront fees for the first couple years. Okay, well, thank you, John. Thank you, Austin and Furman. I really appreciate everyone taking their time today to get together and listen to this excellent webinar. If you have any other extra questions that you think about later, you can go ahead and email them to this agency patent licensing email located on your screen here. And with that, I'd like to say, have a wonderful day.